Okay. Morning, everyone. So let's pick up again talking about resistance networks. So last time we sort of went through and filled out this table, right, that has the heat rate equation, the resistance, that is the jump in temperature divided by heat rate, as well as the heat flux resistance, which is jump in temperature divided by the heat flux, right? All for kind of the classical sorts of problems that we've been talking about. The plane wall in Cartesian coordinates, so a plane wall of area A and thickness L. I put an L sub x over there to differentiate it from a cylindrical wall that has a length of L and inner and outer radii of R1, R2, and for a spherical wall with inner and outer radii of R1, R2. Additionally, remember that we can sort of repaint this convective heat transfer that occurs at a surface area A as a resistance as well, whether a thermal resistance or a heat flux resistance. So using the values in this table, it's really easy to sort of, if you have one wall next to another, and convection on both sides, for example, you just look up the assorted values in here, paste them all together to come up with a composite total resistance, and then use this equation or this equation, right, to figure out, if you know the temperature jump, figure out Q. If you know Q, figure out the temperature jump. That's the case in one of the homework problems on homework 3. And so it becomes a pretty simple exercise. It takes it from boundary conditions all over the place to a very simple process of just algebraic, or rather arithmetic operations. So the example we left off on the last lecture was this case where we said we have a copper tube with a 2 centimeter inner diameter and a 1 millimeter wall thickness, so typical of something you might see in a water supply line in a house, for example. So we're saying that the air around the pipe is at 293 Kelvin, about 20 degrees Celsius, with a convective heat transfer coefficient of 5 watts per meter squared Kelvin. And then we're saying we want to figure out what the heat loss through a 10-meter long section of this is. If we include this blue wrapping of insulation, which is has a conductivity given here, and is 3 centimeters thick, and B without that. So if it was just the bare pipe. All right. So what we did before was we said, all right, let's look at our two sort of our resistance networks that reflect this situation. So as before, we start with a node which indicates one of our known temperatures. In this case, we'll let this be the inside temperature, TS1, which is 373 Kelvin. The resistance of the copper wall of the pipe, we'll say, is R1. That gets us to TS2. So say we get TS1, TS2, or rather than TS, we'll just say T2, TS3, and then T infinity out here. So the next node is T2. The next resistance there is the resistance of the insulation. So this gets us to TS3, and then we have the resistance that reflects that convective heat transfer to get us to T infinity. Okay, so that's with the insulation. Without the insulation, it starts out the same, TS1. Got R1 due to the pipe, but rather than have an R2, it just goes straight to convection. So we end up with T infinity. So really all we got to do is look at the problem in these two situations, right? And evaluate what R1, R2, we'll call this one here RC3, and then this one we'll call RC3 we'll put a star on it. Now this is the kind of the parting note from the last lecture. If you consider these two cases, right, we've got one where we've got this insulated tube and one where it's uninsulated. This RC3 term is going to be different between the two. Right? The convective resistance is going to differ because, if we roll back to this slide, the convective resistance, right, is a function of the surface area of the object. So with the bare pipe, it's going to have a smaller surface area, which means it's actually going to have a larger convective resistance than the insulated pipe, which has the larger surface area. So we can go ahead and say, let's go ahead and make a little table here. Say we've got, oops, R1, R2, RC3, RC3 star. So R1 is just going to be equal to ln of, right, if we go back here, the resistance of a cylindrical wall, like L, we're going to use this equation. So we end up with ln of R2, which is going to be, if this is 1 centimeter radius and this is a 1 millimeter thick wall, then we end up with (1.1 centimeters). So, so R2 over R1 here, the outer right radius of the pipe divided by the inner radius, is going to be ln 1.1. And yeah, over 2 pi times K watts per meter Kelvin times I'm missing a number there. Times the area of the pipe, is that right? No, 2 pi LK, my bad. Okay, 2 pi LK, so that's 10 meters. Okay, so this is going to work out to a number of, okay, then R2, we'll just wait till the very end to add them all up. R2, that is, so if this is R1, R2 is the resistance of the insulation, so similar thing here, but this is going to be ln of, now if it's 3 centimeters thick, that's going to be 4.1 over 1.1 divided by 2 pi times 0. What was the 0.055 watts per meter Kelvin times 10 meters. RC3 is going to be equal to 1 over 2 pi times 4.1, 0.041 meters times 10 meters times 5 watts per meter squared Kelvin, and RC3 star equal to 1 over 2 pi times 0.011 meters times 10 meters times 5 watts per meter squared Kelvin. Sorry, I got a little cramped there. But all I've done is gone to that table and plugged in the assorted values. Not sure if I have all the intermediate numbers written out here. I do. Okay, so if we plug these numbers in, right, and then these two series representations, right, this guy at the top with the insulation gives us a final resistance value of 0.458 Kelvin per watt, and this bottom guy gives us a total resistance value of 0.289 Kelvin per watt. So right off the bat, we can see that, including the resistance does bump the insulation does bump the resistance up, which is the general idea of insulating pipes, right? You want to make it harder for heat to travel through those pipes. So for RT with insulation, I'll go ahead and restate this, is equal to 0.458 Kelvin per watt, and RT without insulation is equal to 0.289 kelvins per watt. Then Q, go ahead and say Q ints here, is equal to TS1 minus T infinity over RT, let's say ints, and works out to 80 Kelvin over 0.458 Kelvin per watt, or 174.5 watts. Okay. If we left the pipe uninsulated, we end up with TS1 minus T infinity over RT, which is equal to same temperature difference, right? Boiling water inside, 20-degree air on the outside, but with a much smaller resistance, 0.289 Kelvin per watt. This would give us 276.5 watts. So we, in this case, just by wrapping right at 3 centimeter, about a 1 inch thick insulation wrap around the pipe, you're cutting down the shed heat by about 40% or so. This should be pretty obvious, right? This is why you see foam wrapped insulation all over hot water pipes, etc. But something that's less obvious is the fact that because of, we talked about how when you use the smaller pipe, your convective resistance will actually be higher because you have less surface area for convection to occur on. When you start putting insulation on, you're actually, you're decreasing the amount of conduction, but you are increasing the ability of it to shed heat by convection. And so that begs the question, you kind of have these two effects fighting each other, right? So is there such a thing as like the perfect insulation thickness? So let's consider a case where you've got your pipe that you're insulating, or your radial object. It could be a pipe, it could be a solid tube, but it has some radius R1, and then we're going to wrap it with insulation that has radius R2. Go ahead and say we've got a temperature, at this inner surface here. We'll say this is TS1. Say that this is TS2, and then out here we've got T infinity. So, RT is equal to TS1 minus T infinity, and is equal to R, we'll go ahead and say R of the insulation itself, or R conductive plus R convective. So for a cylindrical tube or cylindrical wall, the conductive insulation will be Ln of R2 over R1 over 2 pi, whatever the length is, times the thermal conductivity, and the convective resistance 2 pi R times L times the convective heat transfer rate. So we've got these two different components. And if we were to draw a quick little graph of these two things, right? Let's say that here's R2, right? If R2, or so we'll say R2 minus R1. So that's the thickness of the insulation. Okay. So R1 is fixed. We're going to say this is for some constant value of R1. You picked a tube or a pipe or something of some size. How big how large do you need to make the insulation in order to get some benefit from it? Because what you're going to see is, if we call this, let's go ahead and draw this first term as a blue line, right? The Ln, if R2 minus R1 is equal to 0, that's R2 over R1 being equal to 1, and we end up with a value of 0. And then that natural logarithm is going to have a curve that looks like this. This convective heat transfer resistance, however, our R is on the bottom, so it's going to behave as sort of a 1 over x behavior. I should say that this is going to be resistance. So this is going to look like this, right? And if we're adding these two effects together, right, then we're going to end up with something that looks like this. So this tells us that right here is a thing called the critical radius. And the critical radius, if we look at this, we say, well, our idea was, can we possibly optimize our insulation thickness? Okay? And the answer here is no. If you keep going out to an infinitely thick layer of insulation, this term can only get so small. It can never quite reach 0, but it's going to try really hard. This term, however, will continue to grow, and there's no limit on that natural logarithm term, so it's going to continue to go up and up and up infinitely. All right. So there's no maximum on the total resistance. However, there is a minimum, which means that this critical radius is the worst possible choice you could make for insulating a pipe, because it'll increase the amount of convection without balancing that out with reduced conduction. So if you are for R less than R critical, right, the total, we'll say, heat loss will increase as you make the insulation thicker. For R greater than that critical radius, heat loss will decrease as R2 is made larger. And so you can actually solve for R2 by taking the critical or the total resistance here, taking the derivative with respect to R2, and then finding where it's equal to 0, so deciding whether it's a minimum or maximum, etc. I'll save you the trouble. For cylindrical walls, R critical is equal to K over H. And for spherical walls, R critical is equal to 2K over H. So these are those boundaries that demarcate where you need to make sure your insulation is at least that thick, right, in order to actually see any benefit from it. Out here at 0, you're going to have better if you don't insulate it at all, you're better off than anything that's over on this side of our crit. Even over on this side of the critical radius, you might still be seeing a net loss due to your added insulation, but at least it's heading in the right direction as you keep adding insulation. So this is a practical thing to keep in mind when if any of you own homes in the near future and decide to go try to save some energy, and it goes the wrong way. Okay, so extended surfaces. So let's quickly kind of hark back to our rate equation for convective heat transfer. Right, the Newton's law of cooling says, right, that Q is equal to A H T S minus T infinity, where we've got some surface that has area A, it's at some temperature T S, and out here we've got some temperature T infinity. So this is telling us the rate at which, right, we end up with convective heat transfer outward from that surface. So what can we do, right? In many cases, right? The examples we just talked about were how do we minimize heat transfer, but what if we want to maximize heat transfer, which is the case in a lot of engineered systems, right? We generate heat because the things we build aren't very efficient. How do we get rid of all that extra heat so we don't melt stuff? Convective heat transfer is the most common way because everything we do is surrounded by a fluid of some sort or another. So ways to maximize convective heat transfer. Well, you can decrease T infinity, right? Put it into a colder environment. This is often impractical because the ambient temperature of the fluid that we're trying to cool something in is often outside of our control. It would be pretty miserable if you were only able to drive your car when it's exactly 63.4 degrees outside. You can try to increase H. This means, we'll see more later, right, when we start talking about convection, but usually this means doing something like using a different fluid or using a fan to force the fluid's velocity over the surface to increase. This is usually not worth the effort because, like I said, we can't control what fluid we choose to work in, and also adding fans and such requires extra power. And often that extra power doesn't merit the increased heat dissipation. We can also try to increase the surface area. And this is the whole idea behind extended surfaces. So if we can replace a surface like this, right, with one that crams a lot more surface area into the same sort of machinery, for example, if that's our solid surface, then by encouraging airflow across these stacked surface areas, then we can get a net increase in the amount of convection to occur out. But the mechanics of this are a little bit complicated, right? Because so far we've been talking about one-dimensional conduction, right? Heat goes in one direction through the solid and it leaves through some surface. As soon as you introduce this sort of complication to the geometry, you have, right, you're going to have essentially conduction is causing a distribution of, or diffusion of heat to occur inside of the solid. So we've got conduction, and outside we've got, right, heat being convected away from every exposed surface through convection. So it's not as I said, it's not quite so straightforward. And so it requires us to look at the heat equation sort of with a new set of eyes. Engineering applications for extended surfaces are all over the place. So anytime you see things like heat sinks on electronics, right, the whole purpose is to conduct that thermal energy through a greater surface area so it can get pulled away by the gas. The radiators in your cars or the cooling fins on air-cooled engines, right? The whole purpose is, once again, the redistribution of that thermal energy to a greater surface area so it can get wicked away. All right, so we're going to step through this process. Exactly once, so you can see why the so-called fin equation is something that we've got to be aware of. So we're going to call this a general conduction analysis. And extended surfaces. So to start things off, we're going to be looking at a type of extended surface, or we're going to do the derivation here, rather, for a type of extended surface that's known as a pin surface. So imagine this sort of conical this conical extended surface. So out here we've got some solid base into which is integral this circular protrusion that decreases in cross-sectional area as we move away from the base. Go ahead and give this thing an axis. We'll say that right, this is the positive x direction, right, heading down the axis. As I said, this is what's known as a pin type fin. So what we're going to do is take a slice through this through the surface. And bring this out and treat it as a control volume. So this surface here is what we're going to call the cross-sectional area, which is a function of x, right, because it decreases along the length. We're going to call this little the side area here dAs. So this is a small differential surface area. And it is going to be, we'll say that it is dx thick. Okay. So what about heat balance or energy balance on this little slice of our fin pin? Right? We've got heat coming in. We'll say this is Qx. We've got heat coming out. We'll say this is Qx plus dx. And then out from this, and so that's what's flowing through this cross-sectional area, right? Out through the exposed surface, this region here, we've got some rejection. We'll say this is dq convective. And so for the sake of completeness, we'll go ahead and define stuff. AC, this is the cross sectional area at x and ds differential exposed surface area. Okay, I want to make one little note here in terms of what we're going to be assuming here. So note, we are assuming that the temperature, right, is still a function only of x. So I mentioned before that when you have fins, it's not, strictly speaking, a one-dimensional heat transfer problem anymore. And that's the case here because right now we're assuming that convective heat transfer is occurring through surface in directions other than x. But we're still going to assume that the temperature varies only along the x direction. That is, the temperature across each of these faces is going to be assumed constant. And this saves us from the trouble of solving this in 2 or 3 dimensions. And it's also usually a really good assumption whenever you have a fin where the thickness, right, or in this case the radius, is a lot smaller than the length. So this is a good assumption for long, thin fins, which is generally most types of fins that we see in actual engineering practice. I have a feeling we're not going to make it back to this, so was that it?
It usually tells us.
Yeah. Huh?
I'm fine with biscuit.
All right. Yeah, it's probably somebody. I don't know. Unless it starts yelling at us, or someone else comes in and yells at us, or we see flames. We'll. Then. Yep. So, all right. So, energy balance on this. Let's try to finish this up quick so we can run if we need to. So the energy balance on this, right, is basically the total stored energy is equal to the total energy in minus total energy out. We're going back to chapter 1 here. So we're going to assume that the whole thing's at steady state. So that goes to 0. And then we're going to start pulling out, in this case, the energy in, E dot in total. This case is just equal to that Q dot X term, right, that we see at the left, moving in, and our E dot out total is equal to Q X plus dx plus dq convective. So, a couple of intermediate steps here. So plugging those in, we end up with 0 is equal to qx minus qx plus dx minus dq convective. All right. Anyone remember how we dealt with this term before? First order Taylor series. Perfect. So first order Taylor series for qx plus dx basically tells us that qx plus dx is equal to qx plus partial x qx times dx. And then, right, if we wanted to take it to something other than a first order, we would add higher order terms, but we don't want to do that, so we'll go ahead and leave those off. And then our Q convective, right? We can go ahead and take care of that using Newton's law of cooling. BQ convective is equal to H times D AS times T at that location minus T infinity. Where if we write the DAS is this exposed surface area that is losing heat transfer, or that is losing heat by convection. So if we plug those in now, we end up with 0 is equal to Qx minus Qx plus partial x Qx dx minus H T minus T infinity DAS. Looking over here, these Qx's are going to cancel one another, and we are going to end up with negative partial x Qx dx minus H T minus T infinity DAS. Okay, so now we're going to go ahead and use, on this guy, we're going to use Fourier's law of conduction, which says that Qx is equal to negative K A partial T partial X. Well, say AC, because that's the nomenclature we gave to the cross-sectional area. All right? So conductivity, temperature gradient on X, and cross-sectional area normal to the X direction. So plugging this in now, we end up with 0 is equal to K D dx. Oh, sorry. It's going to just be ddx of K AC T dx minus H T minus T infinity dA S dx. I should note here that we divided through by dx. Okay, everyone with me so far? I just plugged in the rate equations from chapter 1, and I divided this whole thing by d sub dx. So it came out here, and it went under our d a sub s. So if we look at this term, right? Let's consider our pin fin once again. Right? If this is x, and this entire exposed area up to that position x is S, right? We could write that A sub S is equal to the integral from 0 to x of the perimeter of that object times dx. So taking the derivative with respect to x gives us the local perimeter of that fin. So in this case, it's just the circular perimeter. We're going to leave it in P, though, because this is valid for any other shape. It can be a circle, an ellipse, a rectangle, what have you. So plugging that in, now we end up with 0 equal to partial x, KAC, x minus h p t minus t infinity. So on this guy, we're going to go ahead and assume that k is constant. Okay, so k can come outside, and then we're going to apply the product rule to the argument of this derivative here. 0 is equal to partial x, or k, partial x, AC, partial t,
partial x plus AC partial squared t partial x squared minus h p t minus t infinity. And go ahead and divide through by k times AC. AC plus, oops, that's gone, t over dx squared minus hp over k c t minus t infinity. Okay, so now let's just do a little bit of rearranging to clean it up. So what we essentially have here is partial t, partial x, this is squared, plus partial AC, partial x times 1 over AC, partial t, partial x, minus HP over KAC, t minus t infinity is equal to 0. And we'll call this the Finn equation. So I know that that was a lot of sort of rapid fire manipulation, but in the scheme of things, right, it just said we're assuming that heat flow occurs in the x direction and that convective heat transfer occurs through the outer surface. Do an energy balance on a tiny little piece of it, and plug in the rate equations that we should all be pretty comfortable with by now. And through some extra manipulation, we get this. And what's nice about this is, right, t is what we're looking for as a function of x. The cross-sectional area and how it varies along x is usually defined by the geometry of the fin. This is something that we'll know ahead of time. H, K, the perimeter, the cross-sectional area. Again, these are all defined by the problem. And so what it turns into is a second-order differential equation on t. So a second-order ODE with constant coefficients, which is something that you've all come across before. Okay, so right now it has potentially non-constant coefficients because this AC changes. So this has non-constant coefficients. With non-constant coefficients, which I got one step ahead of myself there, which is still pretty hard to solve, actually, because if AC is made a function of x, things get sort of dicey. You have to pick trial functions and start using some more advanced methods for solving it. So what we're going to do is we're going to talk about the solution for simplified fin with the constant cross section. And the beauty of this is, let's say what we're talking about is now, it could be a cylindrical fin, or we'll talk about a rectangular fin. So in this case, right, if we were to take a slice through this, we would end up with AC, which is a constant along x, and the perimeter, right, of the slice is also P is also a constant along X, where X here is defined along the length of the fin. So, pin or sorry, in this case it's a fin. The previous one was what we called a pin fin because it's circular. It's just the name that's given to it by the super smart people that designed them. Okay. When we're talking about things that are not circular, we generally just call them fins. And in this case, you're still not wrong if you call it a fin. It's just a specific type. So the fin equation, right? D squared t or partial x squared plus 1 over AC times partial AC partial x partial v partial x minus HP over KAC equal to 0. Right now, because we're saying that that the cross-sectional area is constant on x, this term goes to 0. We're also going to make a couple of substitutions that'll simplify things. So let's go ahead and it's not necessary to make these, but it simplifies the solution. So we'll go ahead and define what's called the excess temperature. So theta of x is simply equal to the difference of the local temperature from the surrounding fluid temperature. So this is what's known as the excess temperature, right? And if we were to take d theta dx, because this guy is constant, because T infinity doesn't change along x, this becomes the same as partial T partial x. We're additionally going to define this variable m such that m squared is equal to HP over KAC. And so if we plug these substitutions in, what we end up with is partial squared theta partial x squared minus m squared theta is equal to 0. Okay. And now this is a much simpler equation to solve because it is a second order ODE, or second order homogeneous ODE with constant coefficients, right? Because m now we're assuming to be constant along the length of the pin. So the general solution to an equation like this, right, and you've probably seen this from differential equations courses, is simply C1 e to the mx plus C2 e to the negative mx. All right, and just as in the case of the heat equation, which values the C1 and C2 take will depend on the boundary conditions for the problem. So you've got to know something about the temperatures or the heat fluxes at different positions along the fin, and those are the situations we're going to talk about in the next lecture. So that wraps up the pin equation. Yeah. Huh? Is there a y? Oh, that's mx. Yeah, there are no y's in the problem.